So today we're going to continue working with some word problems that we want to use equations to help us solve by creating the equation that matches the situation. So first of all, we need to understand something about motion. So it says here an object that moves at a constant rate is said to be in uniform motion. So look at the image here. You can see there are two cars, and you can see by the arrows that they are traveling in the same direction. One is going 40 miles per hour for 5 hours and has traveled 200 miles. The other is going 50 miles per hour for 4 hours and also has traveled 200 miles. So the things you have to think about are distance, rate, and time. So there is a relationship that exists. There's a relationship that exists between distance, rate, and time, and that's what we're going to be examining today. That relationship is that distance, which is how far you go, is equal to the rate, and rate in this case is speed. So miles per hour generally is what we think about, times the time. So if you go back to that little image that you just saw, you could see that 200 miles is the distance, the rate is 40, and the time is 5. Or 200 miles is the distance, the rate was 50, and the time was 4. In either case, you could travel the same amount of distance with, and obviously, the slower you go, the longer it takes, the faster you go, the quicker it is. And that's what we're looking at right now. All right, so we have a train that leaves the station at 1 p.m. and it travels an average of 60 miles per hour, okay? We have a high-speed train that leaves the same station an hour later, and it travels an average of 96 miles per hour. The second train follows the same route as the first train, but on a parallel track, so you don't have to worry about them running into each other, okay? So the question is, in how many hours will the second train catch up with the first train? So what I'd like you to do is to set up a table, and this is a very organized way to solve these kinds of problems. So pause the video and copy this table down. Okay, so we have train 1 and we have train 2. And if you think about what it is we're trying to find, we are trying to find the amount of time it will take for the second train to catch up with the first train. So this value right here is what we're solving for. Okay, so what we want to do is we want to put what we know into the table. All right, so the first train left at, or took an unknown amount of time. Okay, we don't know what that time is, so we're going to represent it with the letter or the variable t. Now the rate we know was 60 miles per hour. Okay, and so the distance, we know that distance is equal to rate times time, so we could call the distance 60t, right? Okay, and then the second train is traveling 96 miles per hour, but let's think about the time. It said it left 1 hour later, and we want to know when they're going to catch up, so we can represent the time here as t minus 1. And so now we can still find the distance by multiplying 96 times the quantity of t minus 1, which is 96t minus 96, correct? Okay, let me just erase a little bit. So because we're trying to find when they catch up, that means they will have traveled the same distance. So we could establish an equation where the first train of 60t is equal to the second train of 96t minus 96. So now we have one variable of t and we want to isolate it. So when this is the case, I would probably do it this way. I would say subtract 60t from both sides because I want my coefficient to be positive. So we have 0 is equal to 36t minus 96. And then I would add 96 to both sides. And now I'm going to write over here, 96 is equal to 36t 36 t, and then we're going to divide both sides by 36. And I'm just doing this all in a jumbled way. T is 9636, which would be equal to what? 2 2/3, it looks like. I'm sure you got that calculation quickly. So now let's think about what that means. So now, remember, you have to go back to what does the question ask us? It doesn't ask us to find t, it wants us to find the time for the second train, and the second train is t minus 1, meaning that we have to subtract 1 from t. So train number 2, the time is 1 hour and 23 minutes, again, including a unit of measure in your answer. Actually, I should have said 1 2/3 hours. Oh my goodness. 1 2/3 hours, because the time was a function of hours. Okay, on this one, Mary drives into the city to buy a software program at a computer store. It's kind of an old problem, right? Because of traffic conditions, she averages 15 miles per hour. On her drive home, she averages 35 miles an hour. And if her total travel time is 2 hours, how long does it take her to drive to the computer store? So we're looking for time again, because we're looking for how long, okay? So once again, we're going to set this up in a table. So distance, rate, and time, knowing that distance is equal to rate times time. Okay, so this would be to and from the computer store. So what do we know? Well, we know that she was going 15 miles per hour there and 35 miles an hour back. And we also know that it took 2 hours altogether, right? So one way you could represent this is if the time is t for how long it took to get there, then we know that from would be 2 minus t. It would just be the difference, okay? Again, that's very generic how we're doing that, because it doesn't matter what time is. Whatever the time is, you could subtract that from 2 and you would get the time going home. Now, what is it we're trying to find again? How long does it take her to drive to the computer store? So this is, in this case, we are finding t, not 2 minus t. We're finding t. So now we can multiply rate and time. And so we have 15t for 2, and then we have 35 times the quantity of 2 minus t, which would be 70 minus 35t. And we know the distance is the same, right? Because when you go to a store and you come home from a store, you've traveled the same way in each direction. Okay, so now we can put 15t is equal to 70 minus 35t. So go ahead and just solve that equation, and then let's think about your result, okay? So once you follow the steps for solving that equation, you get that time is equal to 1 2/5 or 1 4/10. If you put it in decimal form, either way is fine. And so now let's go back to the question at hand. How long did it take her to get to the store? To the store is just t. And so we would answer that as 1 4/10 hours. Okay. Okay, this is my favorite one. Jane and Peter leave their home traveling in opposite, well, that is not spelled right, opposite directions on a straight road. Okay, so again, this is very theoretical. Like, this would never happen in actuality, that you could go exactly opposite directions on straight roads, right? But it's just an algebra thing. Peter drives 15 miles an hour faster than Jane, and after 3 hours, they are 225 miles apart. And now what we're trying to find is how fast were each of them driving. So once again, set up the table, because this really is the very best way to keep yourself organized on these kinds of problems. Okay, so I would probably put their two names, Jane and Peter. Okay, what do we know? Well, Peter is driving. Okay, well, we're trying to find how the rate, right? How fast they were driving. So we have an unknown R, okay? But we do know that Peter is driving 15 miles an hour faster than Jane. So whatever Jane's rate is, Peter's would be 15 more than that. Okay? All right. Now, what else do we know? That they traveled for 3 hours. So the time is 3 for each of them. All right, so now we can do the distance calculation because we have rate and time. So Jane would be 3R and Peter would be 3R plus 45. So now the trick is what to do with that information. No, their distance is not the same, but we do know that their distance is 225 miles apart. So that means one of them has gone less than 225 miles and the other one has gone the difference between whatever that person is and 225 miles. So we just need to add the two distances together to get 225 miles. So the equation is 3R plus 45 is equal to 225. I should move so that you can see that. Okay, so now go ahead and solve that equation. So after you solve the equation, you should always go back and look at what's the question asking. The question is how fast were each of them driving? So if R is equal to 30, then what does that mean? Well, it means Jane was going 30 and Peter was 15 more than that, so he would be 45 miles per hour. 30 miles an hour, 45 miles an hour. Okay. All right. So I'm going to give you some that I want you to try on your own. Let's go to page 108. Let me write this down for you. We're going to do, hold on. Let's try this again. Okay. So page 108. Having some trouble with my screen sharing right now. Page 108, let's do 10 through 15, okay? I will try to write that down here for you. Although I know you can write that down yourself. Okay. One more time. Page 108, numbers 10 through 15. Use that handy dandy little distance equals rate times time chart and you will nail it. All right, see you later.